Hello, my name is Murthy, and I want to take a very important reaction in organic chemistry today called the haloform reaction. Now, you would have heard of iodoform test. No? This iodoform test is actually a class of haloform reaction. Before going into the exact reaction, I just want to tell you the difference between a test and a reaction. A test is something where the product being formed can be identified with the help of the senses, like you can see something, or can hear something, or you can smell something, or you can touch and feel something. For example, you ever heard of Browning tests in your class 10th for nitrates, where you have a brown ring being formed. Similarly, you would have heard of a golden yellow sprinkle test for lead, where you have the PPI2 precipitate being formed, lead iodide. Now coming to organic chemistry, you will learn one reaction called the carbylamine test. It comes for amines chapter. It will come. You'll have isocyanate being formed. It is having a foul smell. So that the smell is the criteria for the formation of product. Similarly, you would have heard of esters, which are fruity in smell. Like benzyl acetate is famous jasmine note. Then you have isoamyl acetate for banana note, etc. So a test is also a reaction, but where we can see or hear or smell or we can feel some product being formed. Now with this basic introduction, we are going to see in more detail what this haloform reaction is. And before going into the reaction, I just want to ask you one thing. Do you have your parents nearby so that I just can greet them, say hi to them? Okay, no problem. If they come, just ask them to stay for a while so that I can just greet them. Okay? Okay. Now let us see what this reaction is. Now for any organic reaction, we need two things. One is the substrate and other is the reagent. This substrate in our case is going to be a methyl ketone, a CH3CO group, or a secondary alcohol with a methyl group like CH3CHOH group. And the reagent is going to be iodine in NaOH, or chlorine in NaOH, or bromine in NaOH. See, chloroform, iodoform, bromoform. You have got 5 members in the halogen family, fluorine, chlorine, bromine, iodine, acetine. Of these, fluorine is very reactive, so we are going to consider it. We cannot control the reaction. Acetine is radioactive. Its nucleus itself is not stable, and therefore we will not be discussing in chemical reactions. Only we are left with 3 options: chloroform, bromoform, and iodoform. Now chloroform and bromoform are colorless liquids, so they cannot be used as a test. Only iodoform is a yellow precipitate. It is having an antiseptic smell, and also used as antiseptic in medicine or pharmaceutical preparations, and therefore we will be having mostly dealing with iodoform test only. Okay, and so the substrate is going to be a methyl ketone or secondary alcohol with a methyl group. It is called methyl carbinol, and if you remember our P block chemistry, we have learnt about disproportionation reactions. Disproportionation reactions are reactions in which the same element will exist in 3 different oxidation states. Like 5 elements we have learnt, that sulfur, phosphorus, and the 3 halogens, namely fluorine, sulfur, phosphorus, chlorine, bromine, and iodine. These 5 elements, they will undergo disproportionation in NaOH. So if you take the case of iodine, it will form NaOI and NaI. So you have iodine in 0 oxidation state forming NaOI where iodine is in +1 oxidation state, and NaI where iodine is in -1 oxidation state. Why I am telling you this is, sometimes instead of NaOH in I2, they will put it as NaOI. So you must be able to identify that even this is the same iodoform reaction. Okay. Now with this introduction, let us see what this reaction is. 1 minute. I have taken acetaldehyde as the reactant, and we reacted with iodine to form this iodoform CHI3. Now we are going to see the mechanism of this reaction, and will normally, in organic chemistry we are not worried about these stoichiometries and all. We just see the important reaction, the reagent and the product, substrate, reagent and the product. But if you understand the mechanism, you can understand, you'll be able to appreciate why we have got 3 iodine and we have got 4 NaOH. So here we have the substrates, which is going to be a methyl ketone or a secondary alcohol with a methyl group. Now you see the first step, this reaction. This is the methyl ketone. You have got the minus M effect of this carbonyl group, and therefore these hydrogens are acidic, and therefore this OH minus, it is playing a dual role. It is acting as both a nucleophile and a base. Now this is something like a combination of your aldol and Canisaro. In aldol condensation, you know that OH minus acts as a base, removing the acidic hydrogens. But in Canisaro reaction, OH minus does not have an acidic hydrogen, acidic alpha hydrogen, and therefore it will act as a nucleophile. So, but here we'll see that since we have got 3 hydrogens, the first OH minus will take, and we must also remember that acid-base reactions are the fastest reactions in chemistry, and given a chance for a nucleophile, it will always prefer to act as a base first. You can also see this in Grignard reagent. If you acted with any acidic hydrogen group, first thing formed is RH. Then only it will act as a nucleophile. Okay, so here we will first react one acidic hydrogen with OH minus. You will have this compound. This compound is called an enolate ion, or you can also call it as a carbanion. But enolate ion is more stable relatively because it has got a negative charge on the oxygen, the more electronegative oxygen. So it's something like a base catalyzed enolization. The enolate ion acts as a nucleophile, and the bromine or the halogen, I have taken bromine here, will act as electrophile, resulting in a alpha haloketone derivative. This alpha haloketone, this is going to be even more acidic because you have got the minus M effect of the carbonyl as well as the minus I effect of the halogen. Therefore, the hydrogen now present in the alpha haloketone is more basic. So you'll have one more round of deprotonation and halogenation, resulting in a dihaloketone derivative. And after formation of dihaloketone, you will have one more round of deprotonation, because now this dihaloketone, it is going to be even more acidic than the monohaloketone. What I mean is here. This is the dihaloketone enolate. This again acts as a nucleophile attacking on the bromine, resulting in formation of a trihalo derivative. This trihalo derivative, now the beauty is that you don't have any more alpha hydrogens. Everything has been substituted by bromine, and therefore now again this OH minus has got no option other than acting as a nucleophile. So now its basic character becomes less pronounced, and its nucleophilic character gets dominated. Now it acts as a nucleophile. Now you have got here SN2 like, this is SN2 like transition state, and this SN2 like transition state, what you have is you have 4 groups around this carbon. When this O minus charge returns, the better living group is only this CX3. So you have this RCOO minus and this CBr3 minus. Now what you have here is the intermolecular proton transfer, whereas RCOOH will give its proton to this CBr3 minus, forming the haloform and the carboxylate ion. So what we ultimately converted a ketone to a carboxylic acid with one carbon less, and the carbon which is less forms the haloform. So this is the short mechanism of this reaction. Now we can think of a lot of mechanism based questions like what will happen suppose we're using NaOD? Where will the deuterium come? Now you see that if you use NaOD, we'll have only CDX3, because this OH, when it acts as a nucleophile, we observe that this H is only coming in the after intermolecular proton transfer. This H is only coming along with the bromoform. So therefore, if you use NaOD, you will end up with CDX3 or CDBr3 in this case. Similarly, suppose we are using O18, that is, if suppose we have NaO18H instead of NaOH, we have NaO18H, then again this O18 will come in the acid. You will have RCOO18 sodium salt. So these things can be answered only if you know the mechanism. Similarly, suppose we are using a 1:1 equimolar ratio of the ketone and the halogen. You would have observed that we have used 3 moles of NaOH for deprotonation and 1 mole of NaOH for nucleophilic attack. Therefore, we have used 4 moles of NaOH. Similarly, we have used 3 moles of bromine for the substituting all the 3 alpha hydrogens. That is why in the balanced equation we are using 3 moles of halogen and 4 moles of NaOH. So suppose if you are using a 1:1 reaction of there is 1 mole of ketone with 1 mole of bromine, then the beauty is that this will become a limiting reaction. What I mean is, 1 minute. This becomes a case of a limiting reagent, because you are supposed to use 3 moles of halogen, and suppose you are having only 1 mole of halogen, then this will get consumed completely and you will have becomes the limiting reagent, and your ketone becomes the excess reagent, and therefore you will be left with 2/3 mole. 1/3 mole of this will react, and you'll be left with 2/3 mole of unreacted ketone. Along with the formation of these compounds, all the things before, you will have a carboxylate ion formed. This is 1 mole, this is 1 mole. Therefore, if 1/3 mole is reacting, this will also be 1/3 mole. The 2/3 mole will be unreacted. Then you will have this again. You will have halogen also, the haloform, and other products. So such questions can be answered only if you know the mechanism. And lastly, coming to the exceptions in this reaction, it is not that all alpha haloketones, methyl ketones will give haloform reaction. It depends again on the other group. For example, in these 3 cases, if you see, you got competing alpha hydrogens, and the groups like cyanide, NO2, they make the alpha hydrogen attached to them more acidic than the hydrogens of the methyl ketone. That is, these alpha hydrogens are more acidic than these, and therefore only these 2 will be removed by the NaOH, and we will not have the haloform reaction. And this is the very famous acetamide, CH3CONH2, and here we will have only this very famous reaction called HBD, or you call it as the Hoffman's bromide degradation, instead of haloform reaction, because here again this hydrogen attached nitrogens, they are more acidic than this alpha hydrogens. So these are exceptional cases, and one must note all these things. We also have exceptions due to steric factors, like this. Have you seen this ketone somewhere? This is a very famous pinacolone. Pinacolone rearrangement. There we get this ketone. Here, this ketone again is you have got the bulky tertiary butyl group, on the other side of the alpha hydrogens, and therefore the third. So here we will end up with the dihalo derivative itself. The OH minus cannot come and remove the third proton because of this bulky tertiary butyl group on one side, and of course here you also have bulky iodines. That's okay, but this bulky tertiary butyl group, that prevents the approach of the OH minus to remove the third hydrogen. Okay, so these are some cases of exceptions. With this, I end this session, and I would like to thank you very much for your patient listening. So student, thank you very much for your patient listening, and after the end of the session, you'll be asked for a feedback. My request is that you please give honest feedback, because it helps in two things. One, I know how much you like the session, and I know where I perform, what are my lacunas, what are the gaps, where I should improve and all. Okay, thank you very much. Thank you.